SwayamPrabha. Digital India. Educated India.
So welcome back. So we were talking about length scales. Then we talked about the rate of transfer of energy. Right now, let us look at the round jet back again. Okay, let us look at, and essentially we're going to write that. Write the energy content of a round jet, and let's see how we will do that. Okay, so the round jet kinetic energy. Okay, now K per unit mass K of the fluid per unit mass right. Right, where of course you know that. Let's write it here. Okay, so is equal to a mean quantity plus a fluctuating one. Right, so okay, let's just say, let's just write this, of course, this way. Let's just write it like this. Right, so this essentially has three components, where U, okay, is essentially equal to a mean quantity and a fluctuating one, and a fluctuating one, and a fluctuating one. This is something that we've, we know this by now, right? And kinetic energy, of course, is kinetic energy per unit mass is essentially this. Okay, now let's just say that this again, right? Let us take a mean, okay, mean of K, right, which is essentially this. Okay, now you can see it is kinetic energy per unit mass is basically half velocity square, and the velocity of course has the turbulent component along with the mean one. Okay, now a mean of the kinetic energy, so let us say that this also is composed of a mean value and a fluctuating one, right? So let's just say this also has a mean value, right? Let's just say that, plus a fluctuating one, right, plus a fluctuating one. So essentially this is the mean component, and this is a turbulent component. Okay, so now mean component, again this is per unit mass, right, is half right. So Ke of the mean flow, so this is, okay, we'll write that later on. Okay, let's just say this is Ke of the mean flow, okay, and K okay, K of the turbulent flow, or K of the mean flow, or the, I think, the fluctuating flow. You know, we sort of, these two together form the turbulent flow. These two together form the turbulent flow, right? So this alone is not a turbulent flow. I mean, this alone is not. So therefore, I'm going to write this as K of the fluctuating flow. When you add that to the K of the mean flow, what we get is the K of the total turbulent flow. I think that's what we're trying to say here. Okay. Now, so essentially, if I were to write that, so then this K of the turbulent flow, right? Okay, before I go, so I'm using this x t, so which essentially means that I am looking at the kinetic energy in the x direction, right? Kinetic energy in the x direction. So when I write this term here xt, so I write that in this fashion. So xt, so I write that in this fashion. So because I'm looking at only the x component, but it doesn't. But of course, the total would mean a summation of all of those, right? So if I were to write it for like all the three directions, then what I would get is half, right, fluctuating part that, right. So this is essentially the total turbulence, the total fluctuating flow, energy of the complete fluctuating flow. To this we add the mean component, which is again u mean square plus v square and w square. So that, okay. So if we do this, right, so then I mean just think about this, that how do I actually go and physically calculate these values? How do I calculate these? This is my understanding, this is my sort of way of describing a turbulent flow, where I have a mean component and a turbulent component, which makes sense to me, and which is gelling well with all the equations that I'm using and understanding. It's fine. But when I go to just think of the pictures of the turbulent round jet that we've seen, now how do I actually go and measure individually these components? How do I actually measure those, right? Individual components of velocity, right? So I think so therefore the next thing to do is basically go and calculate the energy content. So now once you go do the energy content, right, from there maybe you will get some information about the velocity. Okay, let's see if that's the case. Now if I do, so now the point is that what we are saying is if this k, right, so what could be, so when I say that the fluctuating part is this, right, now the question is what is the value? How do I quantify this? What is this, right? So now what this is, okay, that is also one thing. And one more thing is, have you noticed any similarity, anything that is sort of similar to what you've seen earlier regarding these terms? Okay, are you able to recall anything? Let me sort of just pull that up. Okay, let me pull that up for you. let's see, I'm not sure where we did that. Okay, all right, so fine. Okay, so the point is, do you find any, do you recognize these terms? So let me just remind you a little bit. Okay, let me just remind you, and I'm going to write this down, and let me see if you can sort of remind yourself as to what these are. Okay. Okay, so I'm going to write this for you and see if you can remember anything. Okay, so I have written down a matrix of this sort. Okay. 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 Right. So now this was essentially the Reynolds stress tensor. Right. Now, if you see these terms here, right, these three terms, these are right. Do you see that? So I'm looking at the energy here, right. Now, so this is essentially, so therefore I can basically say that this K, right, okay, represents the isotropic part of the Reynolds stress tensor. Okay, and how can I, so and if I write this way, what would you make of it? Okay, now the point is that, which is fine. So now Kxt represents as a part of the Reynolds stress tensor. Now, how much is each of this? What is the value of each of these terms? What is this value in each x direction? So, I guess we're just sort of saying that this is equal to 1/3 of that, right? So, in that case, how should I write this? 1/3 of that. So, this is my Reynolds stress tensor. So, I'm going to write this as right, 2/3. Okay. Right. So now what this is, this basically becomes the Reynolds stress tensor. Okay. So what does this mean? So if I isolate part of the, so this is the part. So essentially what I'm trying to say is, if I take the energy, right, if I take the energy, then I can get the Reynolds stress tensor from the energy. So if I'm able to calculate the, say, the fluctuating part of the fluctuating flow, the energy, the kinetic energy of the fluctuating part of the flow, then from there you can get the Reynolds stress tensor. That's what we were just saying, right? That how do you go and individually calculate these fluctuating values, right? How do I go and do that? This is my sort of representation of a turbulent flow. But then how do I go and actually calculate this, from a given flow? So what we're doing is, if we can actually calculate the kinetic energy of the fluctuating part of the flow, then from there I can get the Reynolds stress tensor. Right? So you can see that now the point is, how much of these is each value? U dash square and V dash square and W dash square. How much, what is the value? Well, we're basically saying it's 1/3 of the total kinetic energy of the fluctuating part. It's just 1/3 of that, right? So I can write that also here. Okay, this is equal to 1/3 of the total K of fluctuating part of the flow, 1/3 of that. Okay. So therefore, if I multiply this by 2 and by 1/3, and this is the Kronecker delta, right. So if I is equal to 1, the I is equal to j, then it becomes 1, right. So which is what we will get here, and if not, then becomes 0. Right. So that's how I should be able to get these values. So essentially, we're saying it is 1/3 of the total Ke of the fluctuating flow. So that is the relevance. Let's put it that way, of the I mean, if I'm able to calculate. So the Ke, actually the fluctuating part of the fluctuating part of the energy of the fluctuating part of the turbulent flow actually represents the Reynolds stress tensor. Okay, it represents the isotropic part of the Reynolds stress tensor. That is interesting, right? As you can see here. Okay, so you know that, like, when I'm not going to write that. So I mean, for the Kronecker delta. Okay, so that's that. Okay, all right. Now, the anisotropic parts, which is like these two, right. Now these also scale. These also. So this is like 1/3. We said 1/3 of the. These three values are basically 1/3 of the total kinetic energy of the fluctuating flow. Now these two, the anisotropic ones, also. So these two. Okay, also scale with the kinetic energy of the fluctuating part. Okay, so anisotropic components of the Reynolds stress tensor also scale with the kinetic energy of the fluctuating flow, which is represented as K, right. So how, well, you get, this is experimentally proven. So you have this, right, this is about 0.27 times the total Ke of the fluctuating flow. That is interesting, right. Okay, so essentially for the round jet, we have written out the energy per unit mass, right, of the round jet, and we wrote that, and we wrote this expression, the mean kinetic. Then we wrote the mean kinetic energy as a mean part and a turbulent part, right. And we see that this turbulent part actually represents the isotropic part of the Reynolds stress tensor, right. So if I can actually calculate this part, I should be able to get the Reynolds stress tensor, right. And of course, the velocities are, for the turbulent flow, are represented as a mean value plus a fluctuating one, right. Okay. Now let us look at this. Okay, we're going to do two things here. Okay, so this is interesting because we are actually looking at the equations, right, and when I do the equations, right, when I write out the equations, I'm able to get some information about the actual physical processes which is taking place in a turbulent flow, right. So therefore, if I have a turbulent part of the kinetic energy, it represents the isotropic part of the Reynolds stress tensor, right. So similarly, now let us look at this. Say instantaneous kinetic energy. Okay. Now, okay, let us see. I'm not going to go into like too much detail into the mathematics, but just about to give you at least some idea, right? And you will of course need to do the detailed math when you take this up as a research topic and you decide to write codes on it, etc. Okay. All right. So now this is from, now I can write as, say, velocity. Okay. Right, this is by definition, right, is equal to energy, right, which is equal to gradient this. Okay. Now, I'm going to just sort of, okay, is equal to right, and tau ij is a stress tensor. Okay. Okay. Now then, okay, so TE dt, so T dt is equal to right, minus okay, therefore TE dt is equal to d dt minus del of this, right, is equal to right, where Sij is equal to right, and this is nothing but the rate of strain tensor. Okay. So tau of course is a stress tensor and S, right, is essentially the rate of strain tensor. Okay. And for a Newtonian fluid, this is all from so Newtonian fluid now stress, right, is equal to right, right? This is again the Kronecker delta. So you can see that if I is equal to 1, so you will have essentially no, in the normal directions, right? II, so XX, YY, ZZ, okay. So this is again an Sij is again the rate of strain tensor, right? Now from therefore from this, okay, so the mean, so the instantaneous, so the Navier-Stokes, so we get this from the Navier-Stokes equations. Okay, this is essentially the flux of energy, yeah, okay. This is equal to okay. Okay, and I just wrote down what Sij is, which is right here. Okay, so I'm not going to repeat that. Okay, so this is rate of strain tensor, right? And Ti, okay, right, minus 2 right. So this is nothing but the flux of energy. Okay. Now then what we do is we integrate 1 over a control volume, right. So we now what we do here is integrate 1 over a control volume. Right. So if I do that, what do I get? Okay. So I'm using this as a symbol for volume integration, right? So this is the same as, okay. So I'm going to just use this. Okay. So T dt, okay, right. So this is the total energy over a incremental volume. So and I do that. So I take the energy contents of the total volume, right, and take a time derivative of that. So d dt of this, right. Now to this, what I do is, this is the surface. This is a surface integral where I do this. Right? Now this is equal to something. Now what is going on here? Okay, as you can see, this is the flux, right, and this is the convective. There is actually flow happening across the across the surface, and so we take the energy transfer due to the flow across the boundaries, which could be into the control volume or out of it, right. So the flow due to the flow moving in and out of the control volume surface, so that's happening. So this is taking care of that change, right, and this is the flux, right. This is the flux, which is flux of energy which is happening across the surface. So that's what that means, right, and that I can write again. I will just integrate, right. So which is over the volume, which is volume, right. Now, so then here this term, right. So, this term here, this one, okay, let's just write down, it accounts for, yeah, so this actually accounts for inflow, outflow, right, and work done, right, on the control surface. Okay. So, essentially it represents the transfer of energy from one region to the other. Yeah, this flow happening across the surface, control surface, right. Okay. Now, let us look at the term on the right hand side here, right. Now, this S, the strain tensor, right, the strain tensor, let us look at this. So, this is my strain tensor, right. So, if you look at this, right, right. So, this is my strain tensor. So, if you look at this, right, so mostly it is positive, right. So, it is always positive. I mean, this thing is always going to be positive. If that is so, if this is going to be positive, right, and the viscosity, of course, so then this integral therefore becomes always negative, right. So, this is so there's a transfer of energy. This also represents a transfer of energy due to viscosity, right. So, this is a the strain tensor, right. This is the rate of strain, this is rate of strain, okay, this one, okay. So, let us just say this is the rate of strain, okay. Now, this term is, say, terms like right. What does this mean? It is something that we've looked at in the previously. So, if I had to visualize this, so say I have a fluid element, if I have a fluid element like this, I think we looked at this earlier, right, and I say I have to say del u I del, and then I need del u del x, say something like that. So, in this case, so essentially okay. So, this is my del u del x, which is the change in u, right, in x direction, right. What if I needed to do del u del y? Yeah. What if I needed to? So, this could be like a stretching, this is like a stretching of that fluid element, okay. And what if I needed, say, del u del y, right, del u del y, if I needed that, then what would we do? Well, say I have this, right. So, this is the the velocity u is in the direction of this little pipe that I have drawn. Then right. So, this is another u, say this is u2 and this is u1, right, and this is my y, right. So, what this is representing is del u del y, so which is a change in the x component of velocity in a direction which is perpendicular to it, in this case which is y, right. So, then you have something like a rotation of the fluid element, right. So, that is the kind of strain that we are talking about, right. Now, when I take that strain, right, when I take that strain, and what I am doing is multiplying two of these, right. So, let us just say, so then this is sort of giving me that into the volume, right, and I multiply that by the viscosity. So, it is basically giving me an idea of an energy content, right. So, there will be energy required for to do something like this. So, I am taking an integral of all of that, all the for as many INJs that you can think of, or as you have taken, I guess. Okay. All right. So, therefore, the right hand side, okay, right hand side is actually representing an energy content. Okay. So, energy content, so an energy, or you can also if you were to say for example del u del x, I am going to just try, this is going to be just to get you to have a feel for how this could look like. So, say Sij is just this, right. So, then I will have say del u del x, right, this I will square up. Okay. Del v is 3 lengths, in the sense del x, del y, del z, right. So, say length, some characteristic length, right, cubed, right. So, this could be del u del x del u into del u del y, this could be that, So, I can, let me write that then. So, it's this, so essentially that. So, or now let us just write this. So, or it will be del u this thing, then del of some length square, right, into length cube, right. So, if I do that, then what I get is essentially length, right, because two of these will cancel out, into square of the velocity, right. So, therefore, this is like and this is over, so since you are taking del, so you are taking it over an infinitesimal element, right. So, this gives you the total amount. So, now so this is giving you so del, so just think about this, del L u square, okay, and you have a length, okay, and to that, right, to that, so this is what is the unit of u. So, unit of u is meters per second, right, meters per second, and then you take a square of that. So, then that becomes meter square per second square. You multiply that by another length. So, then that becomes meter cube by this, right, and then to this you multiply the nu, right, you multiply the nu, and then what you have. So, therefore, you will see this unit, okay, you can do that the rest, okay. So, this unit is actually, so this then therefore, the right hand side becomes an energy, it is a energy, or you can think of that as say work done, you can think of that as work done, right. Now, so I am just trying to visualize what or trying to understand actually that what this thing actually means, right, what this how am I saying, because on the left hand side, and on the left hand side we are looking at rate of change of the energy change. So, now this should also represent that, so the unit should match. So, that is exactly what I am doing. Okay. So, you can do this exercise yourself. Okay. This is kind of a rough work, I am not going to delete these, you can, this is for okay. So, I am not going to delete this, okay. This is, but this is sort of rough work, so to speak, okay, just to explain myself. Okay. So, right hand side, so now if you see here right hand side, so this part is basically positive, this part is always positive. Therefore, this total integral is negative, which means this is here energy is constantly being sort of energy is flowing into it. That's a sink, right? That's a sink. And so energy, so if I, so in the sense that I could have something like this, right, and I have constant inflow of energy. So is that what it is? Sink, right? Just think about it, it's negative, right? So so therefore this here actually, or you can think of that it is negative. What does negative mean, right? So you can also think of that. So therefore let me just write that. So the right hand side, okay. So the right hand side, okay, which is right. So this is a sink, right, of energy, sink of energy, right, which means that here there is, this is essentially, as we have spoken out, right. So then this is, so essentially this therefore is viscous dissipation, okay, that is conversion of mechanical energy into internal energy. Internal, okay, makes sense. So it's a sink of energy, it's always negative, so there's constant inflow of energy. How is that happening? How is that happening? I mean, constantly energy is going there, and then what exactly is happening to it? That energy, something needs to happen to that. It cannot just stay there, right? So because energy cannot be created and energy cannot be destroyed. So what is the next path now that I see here? So what I see is that this is behaving like a sink, right, which essentially means that the energy which comes in, which of course comes in as mechanical energy, right, it is dissipated by the viscous nature of the fluid, and essentially it is converted from that mechanical energy into internal energy, so that it stays. So it could sort of transfer that. So for example, what does internal energy mean, right? Now mechanical energy, it was basically changing the speed or the movement, the way the fluid particles were moving, right? So from bigger to smaller, right, and they're also dependent on the Reynolds number, okay. But beyond a certain Reynolds number, like we said, at a high Reynolds number, right, so the mechanical energy is very small. So then what happens to that? If it is very small, then what happens, right? So what is happening is it is getting converted by the viscous nature, of the fluid. So essentially this viscous dissipation is happening, which is converting that mechanical energy into internal energy. So which ends up, what does it do? It just heats up the fluid, right? Essentially heats up the fluid, okay. Okay, I'll quickly do this and then I think we will stop. Okay, now this equation that we had right at the beginning, so let us just, okay, I'm going to write that again, okay. Now let's just say this is the equation that we wrote down, okay. We said, okay, so let's just write it like this. I take mean flow, right? Okay. Okay. Okay, I'm just writing it like that so that I'm introducing this term epsilon here, right? So this one is nothing but this. Okay, this is, I'm just writing out that first equation, introducing this term here. Okay, now let's just say so that, okay, and okay, this, and I'm also going to write out. So essentially this, and now we've also written actually when I wrote this down, okay, I also said that I have a, so this, okay, mean has a mean part and a turbulent part. So I think what I mean here, okay, this one is the mean part. So let's just say I'm going to write this. So this is the mean part. Okay, then I'm going to write this for the turbulent part. Right. So that is okay. This. Okay, and this. Is that right? Okay. So if I do that, now to this I'm going to just add these two, right. So I'm able to write this because we said the, so we took essentially the derivative of the mean, which we took a mean of this first equation, right. So E we said is a mean quantity per a turbulent quantity. So that's where, so I take that and I write it in this fashion. I write as these two equations. Okay. So if I do that, this. So if I put these two together, this P that I've introduced, it will get cancelled out, and this is what we will have. Okay. So let me also write down what Ti means. So Ti mean, okay, is equal to okay. That, okay, and Ti, the fluctuating part is that, okay. We are basically taking the mean, okay. Okay, that. Then what happens? So I've just introduced this term. I've just introduced this term minus P and plus P. That's all. Okay. Now, if you see here, this P, right? This P actually represents that right. So then now if you see this, right, now this term again, right, this term again is mostly positive, right, this is mostly positive. Okay. Therefore, if you look at equation 2, right, this P which is representing this is actually a positive value, right. So, what we have taken here is rate of change of turbulent part of the kinetic energy, right. So, therefore, this is what you could think of this as sort of adding to that, right. This P is actually sort of adding to that. So, I have rate of change of turbulent part of the kinetic energy, right. So, P is, which is mostly this is mostly positive, right. So, if I were to, so this is therefore behaving. So, this one in this case, of course, this one is actually a source. This is behaving like a source. Right. So, this one is this term, right. This term is actually I mean the one in the brackets is always positive. Therefore, this is behaving like a source, right. This is a source, and you can see that we are dealing with turbulent kinetic energy here. So, therefore, we say that this is actually resulting in this production of turbulent K, right, or simply production. So, therefore, this is actually called therefore, this is production of turbulent K, right, or simply production. Okay. So, if you see here, so I could look at this how, right. So, if I look at equation this equation, the first equation here, right. So, this P, right. So, this is actually taking away, right. This is actually taking away energy from the mean flow, right, from the mean flow, and this is actually adding to the it is adding to the turbulent flow, right. So, if you sort of so it removes K, right. So, the production, so if I look at this, so what is happening is it's removing from the mean flow, right, and it is adding it to the turbulent flow. Okay. So, all right. So, we will kind of stop here and take this up again in the next class. Okay. And yeah, so and calculate, I mean and talk a little bit more about this, right. So, essentially we said something about we've been talking about viscous dissipation for some time now, and I think production is something I had mentioned, I think, in the last class. So, this is what we mean by that. Okay. So, in the sense, if you see that this is an equinumerical equation in which I have introduced a few terms and mathematical terms, right, but then this is making some physical sense or physical meaning or throwing some light on the physical processes that is actually happening. Okay. So, there's this back and forth between the math and the physics and the actual understanding of the physical processes. Okay. So, we just started out with these equations, right, and now I see that if I can interpret the numerical analysis in this fashion. Okay. I will stop here and take it up in the next class again. Thanks.